A single pixel of light glides across the James Webb Space Telescope's field of view. That pixel is Pluto, a dwarf planet stripped of its title, yet still radiating secrets. Its frozen plains, like the heart-shaped Tombaugh Regio, show signs of recent geological activity. Nitrogen ice flows, mountains of water ice rise. At this distance, 5.9 billion kilometers from the Sun, it should be a dead relic, but it is not. The mystery endures. Why is this tiny world still alive? In Prague, on a late summer day in 2006, astronomers gather to vote. The question is simple. What is a planet? The answer rewrites textbooks. Pluto, discovered in 1930, no longer makes the cut. To be a planet, a body must orbit the Sun, be round, and have cleared its orbital neighborhood. Pluto fails the third test. It shares its path with countless icy bodies in the Kuiper Belt. The International Astronomical Union coins a new term: dwarf planet. Overnight, the solar system shrinks from 9 to 8. The public reacts with outrage. Headlines scream betrayal. Schoolchildren mail angry letters. The core of the protest is emotional. Pluto was the underdog, the little world that could. But scientifically, the reclassification makes sense. It opens a door to a vast population of similar worlds, each with a story. The irony is sharp. Just as Pluto is seemingly demoted, humanity's first mission to it is already hurtling through space. New Horizons will arrive 9 years later and reveal a world far more complex than anyone imagined. The label diminished. The mystery only deepened. Why does this dwarf planet refuse to freeze into stillness? Why is it still alive? The mystery only deepened. Why does this dwarf planet refuse to freeze into stillness? Why is it still alive? July 14, 2015. After a journey of 9 years and 3 billion miles, NASA's New Horizons spacecraft plunges past Pluto at over 30,000 miles per hour. Its cameras snap frantic images of a world no human eye has ever seen. What emerges from the darkness is not a cratered, frozen corpse. It is a landscape touched by a giant, glowing heart. Tombaugh Regio, a vast plain of nitrogen ice that stretches nearly 1,000 miles across. Its surface is smooth, almost entirely devoid of impact craters. In geological terms, that makes it shockingly young, no more than 10 million years old, a mere heartbeat in the lifespan of the solar system. Glaciers of solid nitrogen creep across the plain, reshaping its surface, erasing wounds left by ancient collisions. Towering mountains of water ice rise 2 miles high, their peaks frosted with methane snow. A thin shell of atmosphere clings to this world, layered with a blue-tinted haze that tells of active chemistry. This is not a relic. This is a body that is moving, breathing, evolving. Even now, at such extreme distance from the Sun, Pluto refuses to surrender to the deep freeze. Scientists stare at the data, the heartbeats, the ice flows, the air churns. Some hidden engine is stoking a warmth that should have died billions of years ago. The images leave one question blazing brighter than before. How does a world this small, this cold, stay so fiercely alive? The heart of Pluto holds a secret, and from 3 billion miles away we are only beginning to hear its pulse. As the Sun slips behind Pluto, a final image captures something no one expected. Against the black void, a thin blue veil appears. It is an atmosphere glowing faintly, layered like an onion skin, stretching more than 200 kilometers above the icy surface. The color is unmistakable, a deep electric blue. Sunlight scatters off tiny particles suspended in the haze, the same physics that paints Earth's sky at twilight. But here, those particles are not water droplets. They are complex hydrocarbons, tholins, born when methane and nitrogen meet ultraviolet light. The atmosphere is 98% nitrogen, spiked with traces of methane and carbon monoxide, yet it is unbelievably thin. Surface pressure is 100,000 times lower than Earth's. By every known rule, a world smaller than the continent of Australia should not hold on to such a shroud. Pluto's gravity is too weak, its escape velocity too low. Yet the haze persists in dozens of distinct stable layers, revealing a dynamic, active system. The blue veil is a paradox, a whisper of warmth and chemistry on a world where temperatures plunge to minus 230 degrees Celsius. It hints at seasons, at winds, at a heartbeat scientists are only beginning to trace. That parting glimpse from New Horizons froze a single moment. But what happens next to this fragile cocoon as Pluto drifts further from the Sun? The question hangs in the blue light, unanswered, waiting for a new set of eyes. Now those eyes belong to JWST. Its infrared spectrograph cannot map the surface the way New Horizons did, but it can sense the chemistry of a world that is far from frozen. The flyby revealed impossible geology. Sputnik Planitia, The heart-shaped basin, roughly 1,000 kilometers across, is not a dead lake of nitrogen ice. It churns. Polygonal cells, some tens of kilometers wide, rise and sink like a sluggish fluid, erasing every crater in their path. This glacial renewal requires an internal heat source. Ringing the basin are mountain ranges built of water ice bedrock. At minus 230 degrees, water ice becomes granite hard. Tenzing Montes and Hillary Montes rise over 6 kilometers high, their steep flanks carved by tectonic stress that should have ended eons ago. Then come the cryovolcanoes, Wright Mons and Picard Mons, massive shield-shaped mounds towering up to 4 kilometers, with central pits that speak of icy eruptions. The slush they once spat out was a mixture of water and ammonia. Crater counts show activity as recently as a few 100 million years ago. On a dwarf planet barely 2,370 kilometers in diameter, such youth is a provocation. The fuel remains unknown. Radioactive decay alone is too weak. Perhaps a subsurface ocean, laden with salts, slowly leaks heat upward. Perhaps clathrates, ice cages gripping methane, release energy as they break apart. JWST's spectrometer can hunt for the chemical traces of this hidden engine. A sudden surge of methane in the atmosphere could signal a new cryo-eruption. As Pluto drifts further from the Sun, JWST will monitor whether the nitrogen glaciers stall, whether the volcanoes fall silent, or whether this tiny world clings to a warm heart beneath the same blue cocoon that New Horizons once captured. But now an eye far more sensitive turns toward that fading world. The James Webb Space Telescope, parked 1 million miles from Earth, swings its golden mirror toward Pluto. It is an act of extreme precision. Pluto is a mere point of light, shining 5 billion kilometers away at the very edge of the solar system. Its apparent magnitude hovers around 14.4, 40,000 times too faint for the unaided eye. From Webb's perspective, this icy dot is a flickering ember against the overwhelming glare of the deep cosmos. Finding it is not the only problem. Holding onto it becomes a feat of celestial choreography. Pluto moves, carving its 248-year orbit. The telescope, designed to stare at the fixed dawn of galaxies, must now track a target that drifts against background stars, creeping by roughly 1.5 arcseconds per hour. The fine guidance sensor locks on with the steadiness of a laser beam, compensating for Pluto's relentless crawl. Even a micrometer's level tremor would smear the precious infrared signature into static. The reward justifies the risk. Webb's mid-infrared instrument can dissect the exact thermal glow of Pluto's surface ices and the thin nitrogen-methane veil above it. New Horizons tasted the atmosphere as a fleeting snapshot. Webb can sip it slowly, night after night. It measures the hazes not as scattered blue light, but as distinct spectral fingerprints, revealing layer temperatures within a single degree. It watches those haze layers thicken or vanish as the dwarf planet recedes from the Sun, its frozen heart now colder than negative 230 Celsius. Something unexpected may already be stirring in the data, perhaps a faint band of ethane that shouldn't be there, or a thermal inversion that builds faster than any model predicted. The telescope that peers into the universe's cradle is now fixed on the small, cold body that refuses to simply freeze over. Pluto's blue cocoon is finally giving up its secrets, one infrared photon at a time. But that whisper of light is almost drowned out. Pluto's faint infrared glow sits at the edge of detectability, a needle of warmth lost in an ocean of background radiation. To see it clearly, the James Webb Space Telescope performs a feat of tracking engineering that rivals any deep space navigation. JWST must lock onto a moving object roughly 5.3 billion kilometers away, an icy speck smaller than Earth's moon. Its angular size is barely 1/10 of an arcsecond. The telescope's ultra-sensitive detectors, designed to catch ancient light from the universe's birth, could be overwhelmed in an instant by the heat of a nearby field star or the constant infrared hum of zodiacal dust. So the guidance system executes a delicate ballet. It selects reference stars from a catalog of millions, then calculates Pluto's exact position and proper motion. The fine steering mirror makes constant micro-adjustments, holding the target steady to within a few milliarc seconds. Even then, the observation is a high-wire act. The instruments use specially designed subarrays that read out data in fractions of a second, preventing pixel saturation while stacking hundreds of exposures. Engineers calibrate each detector pixel by pixel, subtracting the blank sky's thermal fingerprint. They account for stray light creeping around the sun shield and the faint afterglow of JWST's own optics. The goal is to isolate a single, cold world from a blazing infrared sea, to catch the waning warmth of nitrogen ice and methane haze without burning the very sensors meant to decode it. The telescope becomes a shadow hunter, and Pluto, the shadow it cannot afford to lose. The shadow captured, now it must speak. NIR SPEC and MIRI train their spectral eyes on that faint point of light, splitting its infrared glow into a barcode of peaks and valleys. Each dark absorption line is a chemical confession. New Horizons' LEISA spectrometer glimpsed the surface ices, but JWST's instruments pierce the thin veil of the atmosphere itself. They map gases in 3 dimensions: stratospheric methane, tropospheric nitrogen, faint whispers of carbon monoxide. They track isotopic ratios: deuterium versus hydrogen, a cosmochemical fossil that hints at where Pluto's building blocks were born in the ancient solar nebula. The temperature structure unfolds like a thermal ladder, each altitude layer glowing or absorbing at a specific wavelength. Where models predicted a smooth, cooling upper atmosphere, the spectra hint at unexpected thermal structures, perhaps driven by hydrocarbon chemistry, never before confirmed on a world this small and cold. Seasonal shifts become a time-lapse written in light. As Pluto retreats from the sun, the atmosphere should condense, the pressure crashing. But the spectral signatures don't match the predicted freeze-out rate. The nitrogen bands stay stubbornly deep. The methane haze refuses to thin on schedule. Something is keeping Pluto's air alive, a hidden reservoir of energy or an unexpected chemical engine. The data forces a rewrite. This frozen world, once dismissed as a static relic, now defies its orbital script, and the shadow that was almost lost has begun to give up its secrets, molecule by molecule, to the hunter that waited so long to listen. From those isotope fingerprints, a new chemical riddle emerges. JWST's NIR SPEC instrument dissects Pluto's thin atmosphere and finds something unsettling in the methane to nitrogen ratio. Methane, a molecule that should freeze onto the surface as Pluto glides further from the sun, appears in concentrations that challenge some seasonal models. The numbers don't balance. Where is this extra methane coming from? Surface ices, mostly nitrogen, with traces of methane and carbon monoxide, sublimate under feeble sunlight. On a world with gravity barely 6% of Earth's, escaping gases should bleed into space at a steady, calculable pace. Yet the spectra show the atmosphere is not simply leaking away, it is being actively replenished. The cycle is much faster than expected. JWST's thermal infrared data suggests that deep within Sputnik Planitia, the vast nitrogen ice plain, convection cells churn hidden reservoirs of methane upward. Crystalline ices crack and release trapped gases in a rhythm that doesn't match the 248-year orbital clock. This isn't a static freeze, it's a dynamic engine. The haze layers, once thought to be a passive veil, now look like the product of a frantic chemical turnover. As Pluto's distance from the sun stretches beyond 35 astronomical units, the atmosphere should be collapsing, but JWST catches it roaring with activity. The faint world refuses to shut down. Models built on assumptions of slow decay are suddenly obsolete. That same hunter's gaze, which waited so long to listen, now hears a pulse where there should have been silence. That pulse may defy the old rhythm now. JWST's infrared gaze resolves the haze itself, not as a smooth veil, but as distinct stacked layers. These photochemical shawls, forged when ultraviolet sunlight breaks methane and nitrogen molecules apart, stretch upward from Pluto's icy plains. Models predicted a simple picture. The haze should thin steadily with altitude, its density declining like a dying breath as the dwarf planet recedes from the sun. Instead, the spectra show structures that shouldn't exist. At roughly 500 kilometers above the surface, where the atmosphere was presumed nearly clear, JWST detects a dense shelf of aerosol particles. Lower down, near 200 kilometers, the haze appears abruptly thinned, as if scrubbed away by an unknown hand. The numbers refuse to align. Particle concentrations in these unexpected layers vary by factors of 3 or 4 from simulation outputs. One band, caught in a cold trap near 350 kilometers, shows an enrichment of heavier hydrocarbons, acetylene and ethylene, in ratios that laboratory kinetics cannot yet reproduce. The temperature profile, inverted in places, hints at wave activity or sudden condensation fronts that no model had foreseen. This is not mere seasonal adjustment. The very cadence of haze formation, the delicate balance between creation and fallout, is writing its own rules. A silent heartbeat becomes a cascade of arrhythmic beats. The hunter's ear, pressed against the void, now registers not a single pulse but a defiant, layered chorus. Where there should have been fading silence, Pluto's upper atmosphere hums with a physics we are only beginning to read. The mathematics of the orbit are clear. Pluto is now receding from the sun on its 248-year elliptical journey, heading into the deep freeze of its long winter. As it pulls away, solar warmth dwindles. The thin nitrogen atmosphere, born of summer's thaw, was predicted to slowly collapse, freezing back onto the surface in a gradual, silent retreat. The models were unanimous, but the infrared eye of the Webb telescope tells a different story. It captures a snapshot of this critical seasonal transition, and the data reveals a thermal inertia that no current model can fully explain. The upper atmospheric layers are retaining heat in a way that defies expectation, as if the planet itself is fighting the cold. This isn't a simple cooling, it's a complex, layered resistance. Scientists now confront a dynamic system where atmospheric chemistry and temperature are locked in a feedback loop we do not yet understand. This unexplained warmth means the predicted collapse is being delayed or altered entirely, challenging our fundamental grasp of atmospheric physics on small, icy worlds. The winter is coming, as it has for billions of years, but Pluto, it seems, is not going quietly. The silent freeze we anticipated has been replaced by a stubborn infrared glow. James Webb's 2023 and 2024 observations tell a startling story. When compared to New Horizons' 2015 flyby snapshot, the atmospheric data does not align with models that predicted a slow, graceful collapse. Instead, the thin nitrogen-methane cocoon is thinning faster than any simulation dared suggest. Webb's infrared spectrograph peels back layers invisible to New Horizons. The abundance of methane above the haze has dropped by a noticeable fraction in just 8 years. In some cases, the haze layers that once scattered blue light are shrinking in altitude, possibly at a rate of roughly 1 kilometer per Earth year, though this is still being studied. A year-by-year change, not a century-by-century one. Temperature profiles retrieved from spectral fingerprints reveal that the upper atmosphere is cooling at an accelerated pace, squeezing the hazes into tighter bands. Seasonal shifts on a world with a 248-year orbit should creep, but Pluto's air is sprinting. The carbon monoxide ratio, a key indicator of impending atmospheric collapse, may have shifted enough to challenge some existing computer models. Scientists are now forced to confront an unsettling truth. Tiny, distant worlds can change faster than we thought possible. The stubborn infrared glow that refuses to fade is proof. Pluto is not a frozen relic. It is a world rewriting its own story in infrared light. Pluto is not alone at the edge of the solar system. It is merely the brightest face of a vast hidden population, the Kuiper Belt. Thousands of icy bodies circle the sun here, preserved in a deep freeze for over 4 billion years. Some are almost as large as Pluto itself. Eris, nearly the same size but more massive. Makemake, with its reddish methane surface. Haumea, an elongated world spinning end over end. Yet none of these distant dwarf planets have ever been visited by a spacecraft. For them, Pluto is the archetype, one of the only 2 dwarf planets studied up close. If scientists can decode what JWST's infrared instruments now reveal about Pluto's atmosphere and surface, they gain a master key for the entire belt, the drama unfolding in Pluto's thin nitrogen-methane envelope. The seasonal haze layers, the shifting chemical ratios, the atmosphere that may be collapsing faster than models predict, becomes a template. JWST's spectroscopy penetrates the frigid darkness, detecting the same molecular fingerprints on Eris and Makemake. It can track how surface ices sublimate and recondense, building a theory of atmospheric cycles on worlds where a year lasts centuries. What JWST learns here, on the threshold of interstellar space, rewrites not just the biography of one small planet, but the origin story of an entire frontier. The stubborn infrared glow that refuses to fade on Pluto now casts its light across the Kuiper Belt, illuminating a population of worlds that are no longer frozen relics, but dynamic, evolving bodies rewriting their own stories in infrared light. The stubborn infrared glow that refuses to fade on Pluto arrives at JWST not as a crisp disk, but as a single, trembling point of light. This is the honest limit of the most powerful telescope ever built. At a distance of roughly 5.5 billion kilometers, the dwarf planet spans just 0.1 arcseconds across, far below the threshold where the infrared eye could ever resolve surface features. Even with perfect sensitivity, the heart-shaped plane remains a dream. No image will ever show Tombaugh Regio's nitrogen glaciers from this vantage. The heart stays unseen. What JWST captures instead is a spectrum, a barcode of light from the entire globe. Within that solitary point, the atmosphere's chemical identity and temperature structure are laid bare. Methane, nitrogen, and carbon monoxide ices imprint their signatures alongside the thin nitrogen-methane air. The blue haze layers that New Horizons photographed as a delicate shell now appear primarily through mid-infrared thermal emission. The telescope cannot tell whether the haze is thickening over the convective cells of Sputnik Planitia or thinning above the dark equatorial belt. The infrared eye reads the chemical breath of the world, but not its face. This constraint tightens the stakes. Every spectral line that shifts unexpectedly, every ratio of atmospheric compounds that defies equilibrium models, arrives without spatial context. The heart, with its churning glaciers, drives the entire atmosphere. Yet its precise state hides behind the point of light. Scientists must infer the organ pumping the thin air from a pulse that arrives blurred and whole. The infrared glow that refuses to fade now carries the entire weight of an unseen world, and the heart that powers it remains as invisible as ever. The bright heart of Pluto, Tombaugh Regio, refuses to freeze into silence. JWST's infrared gaze now captures the faint breath of nitrogen, methane, and carbon monoxide rising from its cracked surface. Not a relic, not a frozen scar. A living, pulsing engine. Spectra reveal the atmosphere's layered haze, perched at altitudes roughly 500 kilometers above the surface, is thinning, but not as predicted. Models said it would collapse by now, as Pluto swings further from the Sun on its 248-year orbit. Instead, the haze persists, its blue-tinged layers holding more methane ice than expected. Temperatures in the upper atmosphere show a gradient that defies simple radiative cooling. The heart is not just beating, it is resisting. Yet the picture remains incomplete. JWST cannot resolve the surface directly. The heart's intricate polygons, the convecting nitrogen cells, remain pixels of inference. The pulse arrives blurred and whole, as the previous beat warned. The data shows the atmosphere is dynamic, its chemistry changing seasonally. But the exact mechanism that pumps the thin air from the heart's icy reservoir stays hidden. The heart powers the world, but the organ itself remains invisible. Still, one truth sharpens: Pluto is no relic. It is a laboratory where fundamental physics plays out at the edge of the solar system. The dwarf planet, once dismissed as a punchline, now holds the most unexpected heartbeat of all. And that heart, carved in nitrogen and shaped like a valentine, continues to beat, a whisper of warmth in the frozen dark.